Welcome to lecture 26. In this lecture and the next, we will sort of wind up our understanding of primary decomposition and also learn about computing them or some strategies, well, not exactly to program to compute them, but essentially how to use Macaulay 2 or some other computational algebra system to start trying to solve some problems. So we will learn these techniques in the next in this lecture and the next, and also see some examples being done in Macaulay. Okay. So here is a proposition. So most of these results are not, they're sort of building on what in the previous lectures and geared towards being able to compute associated primes, primary components incrementally, okay, like the example that we did in the last lecture. Okay. Suppose that R is a Noetherian ring and I a radical ideal. Then I has no embedded primes. Okay. That is the associated primes of R mod I. So typically there is a often used abuse of terminology. When we say I has no embedded primes, what we really mean is R mod I has no embedded primes. Okay, so please keep this in mind. Okay, so here we really mean R mod I has no embedded primes. This is all of them are just the minimal associated primes. Okay, and the proof is based on the following observation. If we can write as an intersection of if we can write an ideal as an intersection of prime ideals, which are themselves not comparable, pairwise incomparable to each other, to one another, then that must be a primary decomposition. So note that I is the radical of I, and we already observed that radical of I is the intersection of all primes containing I. But if you're intersecting, then we only need to intersect the minimal primes, and that's exactly what we just said in the proposition. Okay. And these are pairwise distinct, and if we can write I as an intersection of these things, and it says that I does not have any other primary associated primes. Okay. Next, so a geometric viewpoint. So this is also what we started with. Okay. So let K be an algebraically closed field, R a polynomial ring over K in these many variables, and I an R ideal. Okay. Then first statement, but first statement has nothing to do with I. For every prime ideal P, Z of P is irreducible. This is really not a new result. I just wrote it down in this to complete this discussion. Okay. So recall Z of P this is what we had at the very beginning called V of P. So this is the set of all A inside Kn such that f of A is 0 for all f in P. Okay. 2. Z of I is the union of Z of P, where P is in min R mod I. Okay. Not just that this is the union, this is So this equality is the irredundant, irreducible decomposition of Z of I. Okay. So the primary decomposition gives information about the irreducible decomposition of Z mod I. And 3, if this is sort of a converse to the earlier statement, if Z of I is irreducible, then the radical of I is prime. So these are not exactly new results in the sense that we are essentially going to rehash arguments that we used earlier to prove this. Okay, so let's prove one. Okay, so one is the statement that for a prime ideal Z of P is irreducible. Okay, so let J1 and J2 be R ideals such that, so whenever we say, let me just remind, so whenever we say topological statements about Z of I, it comes from the topology, the Zariski topology on Kn, which is the same as, because K is algebraically closed, points of Kn correspond to the maximal ideals of this ring. The maximal ideals of this ring is a subset of spec of that ring. So spec has a Zariski topology, which the maximal ideals, the set of maximal ideals, the maximal spectrum of R gets as a subspace topology, and that is identified, so maximal spec is identified with Kn, maximal spec of R is identified with Kn, and that gives a topology on Kn. Okay, so this is always with respect to the Zariski topology. Be ideals such that Z of P is Z of J1 union Z of J2. Okay. But we know that this is equal to Z of J1 J2. Okay. Therefore, every element inside here, therefore for all f inside J1 J2, f is in the radical of P, which is just P itself. So in other words, J1 J2 is inside P. And last time we saw, in an earlier lecture, we saw that if you have a product of ideals inside a prime ideal, this means that one of them is inside J1 is inside P. In other words, Z and then Z of P is Z of J1. Okay, and this is and therefore it is not the other one is not, this is redundant. Okay, so then this becomes redundant. Okay, so you can remove it and then it is irreducible. Okay, so Z of P is irreducible, and the final statement is a sort of a converse to that, but let's prove 2 before that. Okay. So we need to prove that 2 sets are equal. Z of I is the union of these things. So one is for all P in min R mod I, Z of P is clearly inside Z of I. So the left hand side contains the right hand side. Left hand side of the statement 2 contains the right hand side of the statement 2, and for the other direction, okay. So now we need to show that Z of I is inside every prime every point in Z of I is inside Z of P for some P. Okay. So conversely, okay, let so here again it's an abuse of notation. So we'll write let M be in Z of I, okay, where M is a maximal ideal of R. Okay. So at this point we do not distinguish between the collection of maximal ideals of R and the set of points in Kn. So it is an abuse of notation, but we will still do it. Okay. Okay. So this means that it is a maximal ideal, that is M is a maximal ideal containing I. Okay. That's because every polynomial in I vanishes at the point corresponding to M, and therefore the evaluation map vanishes means when you evaluate it you get 0, but the maximal ideal is the kernel of that evaluation map, so therefore I must be in the kernel, which is M. Okay. Maximal ideal containing I, which now implies that this is a prime ideal containing I, so therefore there exists P inside min R mod I such that P is inside M. That's just I mean this is a maximal ideal, this is min, so by definition there is 1, okay, and which now implies that yeah, which is all that we wanted to prove. P is inside M means that M is inside Z of P, which is what we wanted to prove. Every point inside Z of I is in Z of P for some P. Okay, so we prove that. And 3, okay, so we want to prove that if Z of I is irreducible, so assume Zi irreducible, okay, which means that okay, so this is we proved in 2 that this is an irredundant, we need every prime in every element of min R mod I, and we don't need anything further. So Z of I is irreducible means that there will be exactly one element in this union. Okay. So it's irreducible would mean by 2 that the set of minimal primes over R mod I is a singleton by 2. And okay, so this minimal primes over I is a thing, and which now implies that radical of I is a prime ideal. Okay. Because radical of I is the intersection of the primes in this collection, but there is only one, so it is prime. Okay, so that's the end of this proof. So, sorry. Yeah, that's the end of this the proof. Okay. So now we would like sort of maybe we would like to do it ourselves, but we would like with the help of a computer we would like to, given an ideal in an Euclidean ring, find its associated primes or the primary components or some partial information about in that direction. Okay. So let's say we would like to understand how we can solve that problem. Okay, so let me just briefly write these things so that, okay. So one approach which we did last time was, given an ideal, we will try to say, okay, let's try to find associated primes that don't contain an element, or that way we'll try to enumerate all of them. Okay. So given I inside R Euclidean, otherwise a lot of these results don't apply. Okay. We would like to determine, determine associated primes of R mod I. Okay. possibly by looking for primes in associated primes, looking for P in a thing such that, say, P does not contain A for some suitable A. Okay, so P doesn't contain for some okay. So what is suitable? What should be used? All this will depend on the problem. I am not suggesting some programming strategy. I am just trying to give a strategy on how to solve some problems, essentially by hand, but with the help of a computer. Okay, so that's a suitable A, and maybe not just a single A, but many of them. Okay. So so what is the? I mean, how did we know this thing? So P is associated to M, okay, and A is not inside P. This we saw last time. If and only if P R A is associated to M localized at A. Okay, this is one strategy. Okay, but the one of the problems with this is it is not easy to describe to. Localizing is not very easy. One element you can manage, but it still involves keeping track of this map. So this is a problem, involves keeping track of the map R to R A, and then if we want to find, so this is, and contracting primary components. Let us say R mod A localized to R. Okay. This is if you want to find primary components. So this is even otherwise we can, let's say we can find PRA, but what is P, which gives PRA? So these things require some calculation. Okay, so so we would like to avoid doing this by trying to sit inside R itself and working. So that's what we want to do now. So we introduce this idea of saturation. Okay, so proposition R Noetherian, I finitely generated. Okay, I mean I ideal. Sorry, ideal. It is finite. Sorry, what ideal? Okay, let's say P is associated to R mod I, and A is not in P. Okay, so we are trying to find, or in other words, we are trying to find some property of such associated primes. Okay, then P is associated to R mod I colon A n for every integer n. Oh, it's a great example. Okay, and we will see that this is a way to identify primes that are not in, that don't associated primes that don't contain A. We are not there yet, but this is in R, okay, because this is an element of R. This is a submodule of R. The product has to be inside R. So, okay, so I might forget to write we are only discussing ideals and rings. So the colon is always inside R unless I have to. If it's different, I will state it explicitly. Okay. So proof is again one of these standard arguments using that one becomes familiar with after seeing these a few times. Okay. So consider the map from R to R mod I. linear map, not surjective map, not the quotient ring map, but R linear map, which sends 1 to a to the n. Okay. So, some n greater than or equal to 1, a as above. Okay. So, consider this map. Now, its kernel, take this map, its kernel is everything. Okay. So, what is a map? R goes to R a n. So, its kernel is the set of elements R in R such that, so this is, remember, this is R linear, not algebra map, not a map of rings, but of R modules. Okay. R in R such that R a n is inside I, but this is exactly I colon a n. Okay. So, the kernel comes like this. So, hence we get an injective map R linear map R mod I colon a n to R mod I. Okay. Right. So, it now means that and the quotient, sorry, the quotient is maybe one should write it as a short exact sequence. Okay. So, let us go back here. So, this is the kernel of this map, and the quotient is the co-kernel of this map, which is just R mod I plus a n. Sorry, let me just write it in. Is a short exact sequence R mod I colon a n to R mod I to R mod I plus a n to 0. Okay. So, this is what the map is. Now, let us look at, so this says that associated primes of R mod I is in the union of the associated primes here and here. Okay. Therefore, P is an associated prime of R, okay, and P does not contain A. So, where can P belong? P can only belong here, because if P belongs here, then P would contain I and A to the n. So, it will contain A. Okay. So, let us just since P does not contain A, P belongs to the associated primes of R mod I colon a n. Okay. So, this is true for every n. Okay. So, we would okay. So, now definition, again R Noetherian and I and J ideals. Okay. Okay. So, because R is Noetherian, we can look at the following: I colon j, then I colon j square, and so on, I colon j to the n. Okay. This is all colons are inside R now. Okay. So, what is this? This is all the elements of the ring which multiply j into I. Anything that multiplies j into I will also multiply j square, because j square is inside j. Okay. So, we get this, and anything that multiplies j square will also multiply any higher power. So, in particular, so we have this ascending chain of ideal, and these are ideals of R. So, we have an ascending chain of ideals in R, so it must stabilize. So, therefore, there exists n such that I colon j to the n equals I colon j n plus 1 and so on. Okay. So, there is a stable value. So, this stable value is called the saturation of I by j and is denoted by I colon j infinity. Suggestive notation. This is what happens when you take increasingly higher powers of j and it infinity. Okay, and it stabilizes after a while. Okay, so we would prove some properties about associated primes of saturations, but before that, let's just make some observation that is required, that will be useful in proofs or when trying to solve problems. Okay, so write j as j is finitely generated. We are in an Euclidean ring, some a1 through an. Okay. Then I colon j the saturation, the I colon j infinity is the intersection of the individual saturations. So this is a notation just when you take principal element. Okay, we'll omit the parentheses. Okay, so let's prove this. Sorry, I should write proposition. Okay, so this is convenient because if you have to saturate an ideal altogether, we can do it with one generator at a time. So let's prove this. So proof. So recall from our earlier discussion that the discussion about this, that this is actually equal to I colon j to some fixed power, some j large enough power. So let n be an integer such that I colon j infinity is I colon jn. Okay. But I colon jn is anything that multiplies the jth power of n will also multiply the jth power of ai, because ai to the n is inside j to the n. Okay. And this is inside I colon ai to infinity. So the stable value of this family is this saturation. Okay, so this we have this. So this is true for every I. Okay, so this proves one inclusion. Okay, so for the other inclusion, conversely, okay, we'll take a B in the intersection. Okay. So each one of this is, so for all I, for each I, there exists some mi such that I colon ai saturation is I colon ai mi, and so this is the stable value. So we get this equality. Okay. So now let's consider. And we can just take one single m. Okay, so let m be equal to max of mi. Okay, so just take one single m. So now consider j to the nm. N is the number of generators a1 through an, and m is this exponent that you need to go to saturate each one of those. Okay. So what is this? This is generated by a1 to the e1, a2 to the e2, an to the en, where the exponents add up to nm. Therefore, at least one exponent must be at least m. So this now implies that b times j n m is inside I. okay, which now implies that B is in the J saturation of I. Okay. So, this is the other direction. So, we will stop here and we will continue our studying about saturation and how it is related to primary what information it would give for primary decomposition in the next lecture.